Okay, just back.
Long time no see. Yeah.
So I have to.
Yes.
I just like
You can see.
Yes. Literally all yeah, that's like and then the rest. Always be like and no matter something that was lost. Like it's not it's so much less it's like kind of stuff. Basically, and you saw me she literally begging for one and you have a lot of where else I do no, I'm not grabbing it, that's not I know, Sarah, thank you, I don't. Then, I know, it's really good, you know. It's so normal that it's like the first one to the second is didn't matter. It's central. Yeah, it's good. I know that they to the let's say I don't want to think about chili. Yeah. That's kind of crazy. And I was trying to come back and say, that's not ugly, not having. Now I'm trying to, I guess, I don't be. And it's totally. So how'd you do on the first day then?
It's like part of it, I understand, but definitely not in law school. Yeah. Yeah, the ones with the equations that I did. Just like to the healthy spice stuff. Yeah, that's what they can see those basically. He's at a conference right now. Just like yeah, you're not a talent. Yeah, so can I saw the companies, so he's like kind of together, get investors and partners and sort of thing.
So I know this.
Dude, I hate that. But I'm interviewing, just feels like I'm putting myself on the line and then people are like, maybe I don't know. Yeah. Maybe. Yeah, that's not guaranteed. Yeah, I had one yesterday. It was 4 hours long. It was like meet with two people, to meet with two people, to meet with two people, and it was right over lunchtime. I didn't get to eat anything. Suffering. Suffering, dude. It's a so yeah, see if it's like my personality is exactly.
Yeah, this is just those counties.
That's actually.
It was. Yeah, so it's like. That's how John.
And I.
All right. You guys about ready to start? All right, cool. How many people are like normally here? Is this pretty typical?
Yeah.
Okay. Just curious. So for in terms of today's lecture, did he tell you guys that I was like gonna present or
No.
okay, like 50-50. Do you know what like the lecture is about today?
Said it was review.
Yeah, review. Okay, cool. Just making sure we're all on the same page. So today I'm just gonna go over chapter 5. So that's basically just MOSFETs. And then on Tuesday, I'm gonna go over BJTs. And yeah, that's your whole exam. So in theory, like you're learning two new devices. Both of them operate pretty similarly, but they have like some pretty key differences. So shouldn't be too crazy. I was just gonna start off with like some pretty fundamental like understanding questions. So Okay, so can everyone see like the screen well enough to read the voltage levels? Yeah, I can try refocusing. Is that any better?
Better.
Sweet. I really can't see it from my angle. Nope, that's not gonna help. Okay. Anyways, so if you have 0 volts on the gate of a MOSFET and you have like some amount of potential, I just put 5 volts at the top. What kind of ID would you be expecting? This is really rough, high level stuff. Okay, I heard somebody say the answer. Yep, 0 amps. Perfect. And then similarly, how much gate current would you expect? Yep, also 0. Perfect. So if I'm going to draw basically the exact same circuit again over here. But instead of 0 volts, I'm going to stick 5 volts here. What would be my ID? Again, super high level, doesn't have to be accurate. Not an exact number. Yeah, there's an equation, but I'm not looking for like any kind of exact number.
Greater than 0.
Yep, exactly. Greater than 0. So a number, I'll just call it X. Greater than or yeah, just greater than 0. Right? And then similarly, IG. What would you expect for IG? 0. Yep, exactly. And that's the key difference between BJTs and MOSFETs is in this case with a BJT, you would still have 0 current going through. It's not the gate on a BJT, but you would have 0 current going through there. But with a BJT, you would. But with a MOSFET, this still equals 0. So that's a really key difference between the two. And that's kind of just like, if you have that intuitive understanding, you can get, I think, like 4 of the questions on the midterm just off of that concept alone. It's like some amount of current flowing, or sorry, some amount of current flowing when you have potential, no current. Yeah, and like probably 4 or 5 questions just off of that concept. Is everyone good if I erase this? All right, no complaints. Cool. All right, so something a little bit more complicated, something a little bit more like equation based. Okay, that's better. Okay. I would imagine some people have started solving this in their head. What would be your first step?
Is it a NMOS or P's?
Uh, I think there's one PMOS question on the midterm, and it's not super relevant to the problem. Yeah, I'll leave it at that. Yeah. So NMOS. Sorry, 1.5K. How'd you solve that?
The drain voltage 0.5 and the current going to the resistor is item.
is ID. Yep. Yeah, exactly. So ID equals 1 milliamp. So he's just taking these, plugging them over into the circuit, and then he's using just V equals IR, right? So you have a voltage potential on either side. You have a certain amount of current that's already been dictated to you in the problem, and you're solving for R. You'll notice that the gate of the MOSFET is connected up to this node where you already have the voltage. And because, like we mentioned in the last problem, this current is 0 amps, right? Because it's a MOSFET, no current goes into the gate. So at this point, you can just do 2 minus 0.5 equals 1 times 10 to the power of -3 because it's milli, times RD. You divide this by this, and you end up with, oh, yeah. Yeah, 1.5 volts divided by 1 times 10 to the power of -3 is 1.5 kilo ohms. Does that make sense? Roughly? Okay. Saw a couple of head nods. Sweet. Yeah, and you'll notice another trend with the exam is there will oftentimes be more information given than what you're expected to use. So that can throw you off. But chances are you'll start with the simplest possible method, and then you'll work your way to like a more complicated method, such as your ID equation or something like that. Okay, cool. Anyone need me to keep this up here? Mind if I erase it? Cool, good, awesome. Okay. All right, so this is substantially more challenging, I would say, than the last one. Um, what would be your first inclination with this information? Okay, I'll give you a hint. You have, in theory, you would have a note sheet with you. I guess it'll be on paper this time. And on that note sheet, I would suggest putting all of like your key equations. Just lay them out neatly, make it easy to see so that you can move fast through the exam. On that note sheet, this is like your pretty much your number one equation for the MOSFET problems. It's like the one I put at the top and leave extra space around to make sure I can see it more easily. Okay. So from this, what kind of data can you get? Like what would I start crossing off and using?
And there's zero, so you can get rid of that, right?
Yep, exactly. Yeah, so lambda equals 0, right? So this whole thing just goes to 1. So you're just multiplying what's left of your equation by 1. So that simplifies it. Okay, so from what's left, what data can you get?
Yeah, VGS, and then your VG is 0, and so VGS is just VG minus VS, and so whatever you solve for that would just be your negative source, right?
Yep, yeah, so you're on the exact right track. So what he's saying is you have ID that's given to you over here. So 1 times 10 to the power of negative 3 on this side equals 1/2, that's given. Then your Kn is given over here. So that's again 1 times 10 to the power of negative 3. You multiply that by VGS minus VT, which is given up here, squared. I laid out these numbers kind of nicely so you can just kind of get rid of the milli on either side. So you're left with 1 times the 2 that comes from the 1/2. So that's 2 equals VGS minus 0.5 volts squared. So you do root 2, that's 1.41 equals VGS. I'll just kind of lump it. So plus 0.5 volts equals VGS. Okay, so that's 1.91 volts. And from the very first problem, we know that this is the gate, this is the source, this is the drain. I might have forgotten to mention that, but if VGS is from the gate to the source, then we have 1.91 volts being dropped, which means that our voltage at this node becomes negative 1.91 volts. Okay. What would be our next step?
Question, why are we disregarding the fact that it could be positive or negative 1.4?
Yeah, that's a good point. So what you could do is you could solve for both possibilities and then come up with one that like puts it into saturation mode. I didn't calculate those out with these values that I chose, so I'm not sure if both of them would be in saturation mode, and then in which case either of those would be a possibility. Yeah, I don't have a good answer for you there. Yeah, this is no effort November for me. I got a lot of stuff to go on. But for the final, I'm pretty sure there's like only one possible answer for like this style of problem. Yeah.
And
Yeah.
when I usually do these, I do VOB. I know that VOB has to be greater than negative VQ. So that's like it always forces you to choose like the positive thing.
Oh, I see. So you're saying because VT is absolute value. That makes sense. So that's yeah. Sweet. Did everyone hear what he said? Okay. I'm gonna butcher what you said, but basically, VOV, I have the equation somewhere. Yeah, so VOV equals VGS minus VT. And because we have absolute value VT defined, then your VOV is forced to be, or sorry, your VGS is forced to be positive. Something like that, right?
Yes, it has to be. So it means saturation.
Yeah, to maintain saturation. Okay, I'll just leave that there. Okay, so yeah, with the assumption that I chose the correct VGS based off of the VT being absolute value, what would be your next step to find our D? Yeah, our D.
If we assume saturation, then is that equation to solve the
Yeah, I've technically already assumed saturation because I'm using this equation. That's the one for saturation. There's another one that's for triode region. It's similar, but it looks like it disregards your lambda being 0.
You can use BGS to get VD, sorry, VS, and then you can find ID. And then use that ID. So like 6 minus ID times. What's our starter?
Yeah, we already got ID.
That first half should work though. You can get ID. You can BS.
Yeah, that's all right. I'll just oh my bad, wrong notes. Yep. So the answer to this is that your VDS correlates to your VGS minus VT. You'll notice that this chunk here is the same as the interior of this chunk here. So as soon as you've solved for VGS, then you can plug it into this equation because you already have VT, and then you have VDS. So VDS equals 1.91 minus 0.5. So VDS equals that same 1.41 that we solved for earlier up here. Yep. And then from there, VDS is the voltage from drain to source. So this would be 1.41 volt as a delta, which means that your voltage here is, oh yeah, I fucked up the math. That's all right. Is still negative 0.5 volts. Yeah, the reason I say I fucked up the math is because now this device isn't in saturation, but I use the saturation voltage. I'm just gonna ignore it for now and say like, okay, now you got the exact same problem you had last time, right? 6 volts, 0.5 volts. Now you can solve for ID. And then, yeah, whatever that is, if you function it into a calculator. Okay. Yeah, really sorry about the whole numbers thing. I cranked these out really quickly. I got my defense next Tuesday, right after I teach your guys' next class. So I've been mostly focusing on that. Side note, next class is gonna get out 10 minutes early. So just I guess plan around that because I have to literally go run and like set up my defense stuff. Yeah. Okay. Any questions on that other than the fact that I messed up the numbers? If it's in saturation, that's just an equation you can use. Yeah. So that's another really solid one to put on your equation sheet. Cool. Everyone cool if I erase it? Other question?
For RD, isn't the 6.5 on top, isn't it? For I.
Yeah. Getting closer here. Okay. Yeah, so you would crunch these numbers, so 6.5 times 10 to the power negative 3. Wow, I did that wrong again. That's incredible. Yeah, if you're wondering why I always write the equations before I start punching in the numbers, it's because I feel to get the equation halfway through writing the numbers down. Wait, yeah. Yeah. Cool. Yeah, so that's what, 6.5 kilo ohms or something like that. Okay, cool. All right, I'm just gonna go ahead and erase this one, move on to the next problem. We're kind of like cooking through these. Does anybody have any problems that they want me to solve? Like from the homework or just ones that you're curious about? I think I received a message from somebody like last night and then I never got back to it. I don't know if they're here today. Probably not. That's okay. But yeah, if you think of anything before the end of the class, feel free to ask me at any point and I can just answer it real quick. Um, I only prepared like 6 questions, so we're on pace to finish them all. Okay. Does everyone understand what W3 would be in this case? Like what that is referring to?
The width and Q3.
Yeah, the width of Q3. So Kn prime is like sort of related to omega, or sorry, W over L. And then each one of these devices in theory would have either the same or a different W, and then the same or a different L. This correlates back to that ID equation, which is like 1/2 can prime omega over L times, I'm going to butcher this, VGS minus VT squared. And then you got that 1 over minus lambda VDS. So this little front portion here can kind of be extrapolated a few different ways. This one is pretty common, where you have the Kn prime times the W over L. Another really common one is where you swap out Kn prime, which equals mu n cox. Wait a minute. Yeah. There you go. Yeah, your Kn prime equals mu n times cox. I don't think they ever give you like a separate mu n and a cox, so most of the time you'll just see Kn prime here. But then similarly, if this whole term here is replaced by Kn, not Kn prime, that equals mu n times cox times omega over L, or equally Kn prime times omega over L. So yeah, this little like portion here, you'll see it represented a million different ways. Writing down these equations would be highly beneficial. Okay, and then from this equation, this ID equation, this one's great. But a lot of the times they'll ask you to solve for other things inside of this equation. Most notably, your VDS. And like we said in the last problem, your VDS equals VGS minus VT, right? So I'm sure this is in the book somewhere, but in my undergrad, I just rearranged it so I didn't have to keep rearranging it every time they asked for this. And then that equation becomes, or sorry, not VDS, VOV. That equation becomes VOV equals VGS minus VT equals the square root of 2ID over Kn prime times omega over L times 1 minus lambda V ds. There you go. Again, another very nice equation that you can use for all sorts of different stuff. And for our purposes, I believe this is the equation that makes your life easier. It's about the same. So you can solve this one like with this equation or this equation, it'd be about the same. For this example, I wanted to give you this equation, so I'm just going to solve it with this. You'll notice that you have 0.6 volts over Q1 and 1.3 volts over Q2. So you already know your voltage from here to here. So that's your VDS. But since your gate is also hooked up to your drain, you also know your VGS. From the problem, you know VT. You also know your ID from over here. You also know your Kn prime from up there. You know your L from over here. Your lambda is 0, so you can kind of cross this out. And now you're left with just W, which is what you're trying to solve for. Yeah, I've seen like a million different representations of the same problem. Sometimes they'll ask you for like W of Q2, sometimes they'll ask you for W of Q1, but the process is basically the same. Just have to do some like voltage subtraction. So yeah, I'll just go ahead and start crunching the numbers. So your VGS is 2 minus 1.3 minus your VT, which is 0.5, which equals square root 2 times 1 milliamp. So that's 10 to the power of negative 3 over Kn prime, which is 0.5 times 10 to the power of negative 3. Then your W over L. So you just have your W, then you have your L, which is 0.5 micron Micron is 10 to the power negative 6. Or micron, same thing. And then you just crunch until you get W. And that's what we're looking for. Does it bother anybody if I don't like solve these problems? Like if I just leave them in this form? Like y'all are really good at math. You can like rearrange stuff. And you'll probably have those blue calculators. So if you punch all this into your blue calculator, it'll figure it out anyways. Sweet. Any questions from this problem or problem similar to it? Alrighty. Yeah, anybody need this problem still on the board or can I erase it? Oh, question.
Unless we can assume that the land is
Yeah, since you're only given one L, you just assume it's the same L for all of them. If they specify like L3 or L2, then yeah. Cool. Okay. Does anybody notice anything like kind of strange about this problem?
K doesn't have any levels. But KN.
Yeah, that's weird. There's also I should have written an arrow, but I didn't put an arrow there because for reasons. Yeah, just because I forgot. Yep, so that's odd. What else? Yeah,
You don't know.
yeah, you don't know RD, so that makes solving for IB much more difficult.
The 0.2 is less than 2 volts.
Yeah,
It should be high.
yeah, exactly. Oh, so what does that signify?
Triode.
Yep. Yeah, so well, just to repeat what he said, your 0.2 volts at the drain of the MOSFET is less than your 2 volts at the gate of your MOSFET. Because of that, you're into the triode region, so you need to use a different set of equations when solving for the drain current of your MOSFET. Can anyone think of, so this is like kind of parallel to the question at hand. Can anyone think of a way in which you end up in this kind of situation? Yeah, exactly. If your RD is like very large, in comparison to like how much your MOSFET can conduct. So in order to solve this, you're going to need to pull out your triode equations. But before we do that, I'll just write down the signifier for whether or not you're in triode. Yep. So in our case, we got V drain source of 0.2, which is less than VGS, which is 2 minus 0.9. So that's what, 1.1. So we're in triad. In theory, you can have like a pretty large voltage on the gate in comparison to what you have on the drain if your VT is really large, but that's pretty rare. This is a pretty typical situation with a VT less than 1. Okay, so to solve that, I'll just kind of jump into it because I don't really expect many people to know the triode equations. But this is kind of like your equivalent to your bread and butter for the saturation region problems, but for the triode region. So you'll notice that, and I don't know if this is an error in your textbook or not, but the K doesn't have an N. I would assume it would have an N, but for whatever reason it doesn't. Not sure why that is, but something to note. Yeah, and then the other main differentiator is that your VGS minus VT is no longer squared, and it's multiplied by your VDS in conjunction with the fact that you have your VDS squared. So that number becomes like substantially more important than it does in the other equation. Anyhow, so you're looking for ID. It's already set up to solve for ID, so you can just kind of start crunching away. So 2 times 10 to the power of -3. Your VGS is 2 volts minus 0.9 volts times 0.2 volts minus 0.2 squared divided by 2. Yep, one equation. The most difficult thing there is that you have to check for triode. Yeah, some of these problems on the exam are going to be triode. Some of them are going to be saturation. But I figured I should give you like a heads up on the triode stuff. You do have to check. And sometimes it's not as obvious as like, oh, this is weird when I look at it. Sometimes, as Len mentioned, sometimes you have to start solving the problem, and then halfway through, you're like, oh, wait, now this is weird. Why is it not what I expect it to be? And then you have to go back through and resolve it like it's in triad, which is a bummer, but it's how it is sometimes. Okay, any questions on this problem?
How would you do it if you weren't given the drain voltage of 0.2? Like, would it even be possible without knowing RD?
Yeah, so if you knew your RD, that's a supplemental. You could figure it out if you had RD. I don't think they would do that to you though. That'd be annoying. Because then you'd have to substitute your ID for like V equals IR, right? Because you know your RD, you know your you don't know your ID, and you also don't know your VD. So you'd like rearrange this to be like V divided by RD equals all of this stuff. Yeah. Yeah, they wouldn't do that to you. Okay. Yep.
And it doesn't matter for this one since lambda is 0, but I forget, like for the triode equations, is it still just the 1 minus lambda VDS then outside? Is it the same?
Saturation. So this equation I got, I don't really remember where I got it from, but it doesn't correlate with lambda. It's just this. And I can tell you that you won't have to worry about triode equation with lambda on this exam. Maybe for the final, I'm not sure. Yeah, with that being said, the reason why I've always been putting that like 1 minus lambda over or times VDS on the end of all of your equations is because we haven't used it yet. On the exam, you will have to use it. Another equation that's really important for you to know when you do have to use it is VA equals 1 divided by lambda equals absolute value of VA prime times L. Yeah, another really good one to have on your note sheet.
Could you kind of split it between review what lambda means in general? Because I know in our homework, all of the problems were lambda equals 0, so that's what we have to think about.
Oh, interesting. So there's none on the board that had lambda equals something else or VA equals something else?
Unless that happens.
Okay. He said he made this exam harder than he would have otherwise, but yeah, I didn't realize about that. Okay, yeah. So let me go to the equation sheet. I'll write out that equation again and we'll kind of like look at it, right? So this is nothing to do with the rest of this problem. Okay, so just to repeat her question, it's basically what is lambda exactly, and why does it matter? I don't know from a physics perspective exactly why it matters, but just from looking at the equation, you can see that without lambda being 0, then your VDS correlates with your ID. So the larger, or sorry, yeah, the larger your lambda, the more VDS impacts the rest of your equation. The reason why you assume it's 0 is because compared to things that are squared and compared to things that are like really small numbers, it doesn't track super closely because your VDS will remain somewhat constant between like, depending on what kind of transistor you're using, between like 0.2 volts and like maybe up to like 5 volts, something like that. So relatively speaking, it's pretty small. So just assuming, even if lambda isn't 0, just assuming lambda is 0, simplifies your calculations like 5. Yeah.
And it only is impactful during saturation, because it's not included within the triad, correct?
Yeah, yeah. As far as I understand it.
Thank you.
What's VA?
VA is basically just the inverse of lambda. I think it's a different way of saying the same thing. Yeah.
What's the difference between VA and VA? So in textbooks, they say VA is the early voltage, but I don't know if I really got where that last part comes from.
Yeah, so I think the reason why they correlate it with length is because it's early voltage, right? So the length of your transistor correlates with how much voltage you can block with that transistor when it's off. And then the width correlates with the amount of internal resistance of the transistor when it's on. So if you're doing VA, or if you're looking at VA, it would correlate with the length because it's literally longer. Like there's more distance that the electrons have to pass through before it's like through the semiconductor part of the transistor. I don't know if that's a very satisfying answer. But yeah, it's basically just because VA does correlate with L because you can block more voltage with it. Yeah. All right. Any other questions? Cool. Oh, one more.
Alright, good job. So I did, it's like the difference between early voltage, like what that signifies, and then. So. That's, I guess, my question, does it you, or is like a definition? If at all.
Yeah. I wish I studied it more before coming. I don't really understand early voltage that much. Correct me, somebody in the crowd, correct me if I'm wrong, but if you have like a voltage turn on graph of a transistor, so let's say this is your voltage across the transistor from the VGS, so VGS, and then this would be your ID. I kind of understood it where like this is your turn on voltage, then this would be like your saturation region. This would be your triode. Yeah, I'm not sure. I was trying to see if I jog my memory, but yeah, apologies.
Thank you.
Cool. Any other questions?
What's stopping us from bringing like the whole book into the exam? It's like those.
Nothing. Yeah, the main reason why we're switching away from like electronic notes is because people just chat GPT the whole exam. Um, not because we're trying to limit the amount of notes you have access to. Yeah. Yeah, I guess on a side note, in terms of like the next exam, I think it's like A through P or something like that is in this room, and then P through Z, last name, is in the other room. The other room is like kind of far from here, so make sure you show up to the right room. And if you're in this room, nobody's allowed in the back row because it's impossible to see people's screens, like staggered seating, that sort of thing. Yeah,
Are the tables kind of like this? Those-
I'm not sure. I'm not sure which room it is. Cool. But yeah, and he's given like explicit instructions just to like fail people if we see them using other stuff. Yeah, side note. Yeah, conveniently enough, there's nobody in this room that I see who is some of the suspects of this. Yes. Yeah, it's kind of unsurprising though, right? Like if you care, you're probably not going to do that, and you wouldn't be here if you cared, or you wouldn't be here if you didn't care, something like that. Yeah. Okay. Any other questions before we move on to the next one? Okay, cool. Has he taught you guys about current mirrors? Okay, that's a no. Yeah. So again, I knew he was gonna make this exam hard, but I figured I should give you a heads up on current mirrors. Um, I'll just kind of write them out. I think you can do them with BJTs or MOSFETs. I'm mostly familiar with how you do them with MOSFETs. Do they have networking capabilities? I didn't think so either. I mean, you can load Doom on them if you want. If I see you playing Doom, I won't knock you for it. Okay. Can everyone read that? It's kind of messy.
What idea?
It's just 1 volt.
That's on the right side,
Oh, this is I2. Yeah, let me make that bigger. Oh, yeah, that's another thing to mention. I use like I kind of interchangeably with I. So capital versus lowercase. That's a misnomer. I really need to catch myself doing that because capital means DC current and little I means AC current. That'll be important. I don't know if it's important for this class or if it's important for 430, but if you guys take 430, yeah, that's a really important distinction. That's also probably worth putting on one of your note sheets at some point. I have it on mine. Uh, but yeah, I should be using big I in all of these problems, but I haven't been. Okay, I'll just leave it up there. All right. So I'll try and put all the information over here. Okay. So he hasn't taught you current mirrors, but can anyone tell me, like, just use the name as a reference? What is a current mirror? Huh?
Current's the same on this side.
Yeah, some sort of. Yes, but no. Um,
Same but in.
um, let me just elaborate. So kind of also sort of, but let me just elaborate what he said. Essentially what it does is if you have a Q1 and you have a Q2, if they're exactly the same transistor, then you'll have exactly the same current on either side. No matter what's going on with this resistor or this transistor or anything like that. They're used in order to bias the current of like other transistors like further down the chain. And they're really important in 430 for like multi-stage amplifiers and stuff like that. But here's one. So the kind of the trick with them is that if Q1 and Q2 aren't exactly the same transistor, which can be very difficult to achieve because of manufacturing tolerances and stuff, then you're going to have a slightly different current in either leg. You can use that to your advantage. So if you make Q2, let's say twice as large, then you'll have twice as much current passing through it as your reference current. So you could have like a small reference current and a large bias current, just depending on like how you set things up. That ratio is kind of what it sounds like. So if you have the width of Q1 equaling 1 micrometer, then your width of Q2 and Q3 will be 7 times the current that's in your reference. So the equation is pretty simple. Your I2 equals W2 in this case, divided by W1 times IREF. Yeah, actually, I think I might have misspoken. I think your W2 and your W3 always have to be matched. So it just kind of eliminates your resistance there. So in this particular problem, your I2 then just becomes 7 divided by 1. And then you have times 10 to the power -6 on both sides. But those cancel out. Times 10 micro. So your I2 then just becomes 70 micro. Yeah. Any questions so far?
Is there a particular region that Grand Mirror operates in? Is it like a saturation of things? Try it, because it looks like one maybe south, probably saturation and Q2, is it?
Q2, so this all goes down to -1 volt. So sorry, let me think real quick. They're both in saturation, and I'm pretty sure it only works in saturation. Yeah, so you have to make sure that everything operates within saturation, regardless of how your system may swing. Okay. Any other questions on this?
Something like this is going to be on the exam.
Yeah.
Are there any other questions that you can think of that might just be stuff we don't know?
Yeah, the VA stuff is maybe stuff you don't know. This for sure, I guess, is stuff you don't know. I didn't think I was going to get through these questions as fast as I did, so let me take a look. No. I took a step back on purpose. Oh yeah, there's another one that you probably don't know. But
It's remembered for sure.
but you don't need to know how it works. Yeah. Yeah. Huh? No, not for that one. You guys could figure that out. It correlates back to the very first thing I showed you guys. I'll re-show that, I guess, but if you understand like cutoff versus triode versus saturation, you'll be able to understand that one. Yeah. Yeah, so yeah, so there's like something similar to this, and then there's something like similar to this but more difficult. But in theory, you don't need any new concepts beyond what I've already told you, or any new equations. So if you can get this far on this one, you should be able to handle the more difficult one. Yeah.
As far as like the format of the exam, it's gonna be similar to the last one, but will we have like, I don't know, I assume like 2 quizzes on MOSFETs and 2 quizzes on QTs.
Yeah. So it's gonna be 2 quizzes on just MOSFETs, half a quiz on MOSFETs, or sorry, shit. Yeah, half a quiz on MOSFETs, and the second half of quiz 3 is BJTs. So it's 2.5 quizzes on MOSFETs, 2.5 quizzes on BJTs. Why? It's just 2 chapters, right? Like this exam is technically just covering 2 chapters. Yeah. Yeah, BJTs are harder in my opinion. If I prepared some BJT questions, I would show you some because like they will take longer and we have less time next session. But Yeah.
Will we be able to go through about solving the rest of this problem for the voltages?
The voltages?
Yeah, or I'm guessing the label like V1, V3 is probably what we asked to solve for.
Very astute. Yeah, sure, why not? Yeah.
So like, if anything, we can just like take the picture and see the highlights, and like, the saturation. Like, saturation.
I didn't extrapolate any equations. I just kind of was like, it's a current mirror, and this is the ratio that I use for current mirrors. I didn't look at the book or anything to come up with this. I just know this from somewhere at some point. Yeah. But I solved I solved all the equation, or sorry, all the questions using this formula and it worked, so I trust it. Okay, yeah, so we got what, 10 minutes? Sure. So if you were to want to solve for V2, I'm not gonna make this easy for you guys. How would you do it?
I assume this is saturated.
Yeah, yeah, you assume saturation. Pretty much always assume saturation at first. Not always, but
BDS is what it means, minus VT, so for you.
sorry, can you say that louder?
BDS equal to BGS minus VT, so for.
Yes, but how would you get either VGS or VDS?
Have to solve for VT first, so you can use the current vector.
You're saying V1.
We don't have resistance.
Yeah, we don't have R. So you don't technically need to know V1 to be able to solve for V2 and V3.
Solve for VT.
Sure, yeah, let's try that. So V3 is essentially using this equation up here. V3 equals V equals IR. So V3 equals I2, sorry, 1 minus I2 times 6 kilo ohms. So I2 is 70 microamps. Yeah, whatever that is. I'll get my calculator. Or if somebody wants to calculate it for me, I heard a calculator. 0.5? Sweet. Sweet. Okay. Now what?
We probably use the ETS is V3 minus V2. And then GS is negative V2 and you like sometimes you V3 is solve V2, which makes sense and you know.
Yeah, so you're using a property of current mirrors in order to try and solve it. Oh, right, because you're saying that V2 equals V1.
Yeah.
I think that's normally the case. I'm not sure if you have an unbalanced system like this, it is. It might also be that ratio thing. I just don't remember. But again, you don't need V1. Yeah.
So we could do for VGS, the gate on Q3 is 0, so it's just 0 minus V2. And then you could plug in for VT. Yeah.
Like that?
Yeah, I think also, isn't VDS also like VD minus VS and just even V3 be like VD, so you could also put, because you don't know VD yet, right?
Yeah, you don't know VDS yet.
So could you do like, and replace VDS with, V3 minus V2, so V3 is the drain and V2 is the source.
You said VDS equals what?
Isn't VDS equal to VD minus VS? VD would be V3 and VS is V2.
Sorry, and then the VD would be
Drain's on the top, right?
yeah. Drain is on the drain is on the top. Yeah, so that you're saying V3 minus V2. So now we're basically having two equations.
Yeah.
Yep. Yeah, so you could in theory set that equal to each other, right? So negative V2 minus 0.5 equals V3 minus V2. Yeah, so you would end up with V3 equals negative 0.5. Which is probably right, because you can. That's interesting. I think we made a mistake at some point, because I'm pretty sure it's actually.
Isn't that
Point.
equation the one that puts it on the edge of saturation, not necessarily how deep in saturation it is?
This one up here.
Yeah, because that's saying VDS is equal to the overdrive
Mm.
voltage.
Let me check.
So it could be greater than.
Yeah. Yeah, I think you're right.
So it's like the ID like one half. You don't have A. Okay. Oh, we have WL.
Yeah, so you have mu O, or sorry, mu n COX, and you have W over L, and you have that lambda equals 0.
You could use the saturation equation, solve for VGS and then VS.
Yep.
Right?
Yep. Yeah, exactly. I told you guys I'd make you suffer, so. Yeah, so what he said is basically we have the drain current I2, and we have this equation, which is mu n COX times W over L times VGS minus VT squared, and then I won't write the rest of it because we know lambda equals 0. So that's ID equals, or sorry, not ID. It's 70 micro. So 70 times 10 to the power of negative 6 equals 1/2. UNCOX is 200 times 10 to the power of negative 6. W over L, they're both in micro, so I'll just leave that out. But W is 7, L is 0.1. So 0.1 divided by 7 times VGS, which is what we're looking for here, minus VT, which is 0.5 squared.
You did L over W.
Oh, I did? Oops. Thank you. Yep. Okay, so I don't know if anybody wants to solve that, but VGS is this, right? Minus plus VGS. We'll do that in another color. Minus plus VGS. So now you have V2. Yeah, let me know if anybody solves this, by the way. I'm just gonna call it 0.5 because it seems like it'd be about 0.5. I don't know. So that makes V2 equal negative 0.5. Oh, sorry, I can't see because the light behind you.
Okay, for the ratio, sorry, go back to the ratio with the I two. You say W two has to equal W three for that to be true.
I'm pretty sure it almost always is.
Okay.
Yeah, they give you that. Yeah.
Would there be any questions that involve like P five and some say to them?
Yeah. But, yeah. Okay, any other questions?
How would you find R?
R?
Would it just be like when you get the questions?
Yeah, so I don't really remember this relationship super well, but there's something like V1 always be equals V2 or something like that. And then you could just find V1, you know, 1 R, and you know IREF. But because these are not equal resistors or yeah, transistors, Q1 doesn't equal Q2 exactly, then I don't know if that necessarily holds.
What is like something by P2? Five, you base off of. This is itself and negative.
So I say that one more time, a little louder.
Since we found the, can we use like the link will be. Actually. Use V2 to.
So you said to find V3?
Oh wait, we didn't find.
We did find V2.
Okay.
Yeah.
Use V2 to find the.
For R? Yeah, in theory. Again, you'll have to look up that relationship because I don't really remember it, but I'm pretty sure it exists. I'm pretty sure. You'll need to double check me though. Yeah. All right. Any other questions? You're free to go if you gotta go, but any other questions? Yeah.
The gate current always zero.
Yep, always 0. Yep.
No matter the region.
No matter the region, always 0. Yep.
Yeah.
There was gonna be a problem with PMOS and NMOS.
Yeah.
Are you able to find or like get a problem in the Z?
I wouldn't worry about it if I were you.
What, why?
It's covered by the very first thing.
Okay.
Yeah.
Did you record this?
Yeah, I did.
Okay.
I think it should automatically give Dr. Me a notification, but dude, he's doing the